The objectives of the experiment are: first, to evaluate how fluid volume, impeller blade type, rotational speed, submersion depth, and shaft angle influence vortex formation and mixing efficiency. Second, to visually and physically assess vortex depth, shape, and stability under varying operational conditions. Third, to measure and compare mixing performance using tracer bit, identifying the most effective parameter combination for achieving homogeneity with minimal energy loss.
For material and apparatus, our setup consists of a variable speed handler mixer with interchangeable balloon whisk and spring disc impeller, clear beaker mixing vessel, and solid tracer bit to visualize the fluid flow. As outlined in here, the procedure requires assembling the adjustable mechanical mixer and pouring precisely measure 1000 ml and 2000 ml sample of distilled water into the container, confirming the starting height with a ruler.
Based on the result obtained, the effect of water volume on mixing performance can be clearly observed. For the 2000 ml volume, the water height increased from 7 cm to 10 cm, which allowed the impeller to distribute energy more effectively throughout the fluid. This results in stronger axial and radial flow, creating a deeper and more stable vortex of 5 cm. The turbulence level also increased from high to very high, leading to faster mixing. As a result, the mixing time decreased from 9 seconds to only 6 seconds. In contrast, the 1000 ml volume produced a slower liquid depth, which limited vortex development. The energy transfer by the impeller was less effectively distributed, resulting in weaker circulation and a slower vortex of 4.5 cm. Although the turbulence level was still high, the mixing process was slower, requiring 9 seconds to achieve complete mixing. In conclusion, increase the water volume from 1000 ml to 2000 ml, improve the overall mixing performance by produce a deeper vortex, stronger circulation, higher turbulence, and a shorter mixing time. Therefore, a large liquid volume enhance energy distribution and mixing efficiency under the same operating condition.
Moving on to test 2, which investigate the effect of impeller type. For the experiment, the constants are a fluid volume of 1000 ml, medium speed, a vertical shaft position at 90 degrees, and the same depth. With this control, the balloon will produce a deep vortex and strong turbulence, dispersing bits uniformly and mixing efficiently. The spring disc, however, create only a shallow vortex with weaker turbulence, leading to less uniform mixing. Let's break down this finding further in the discussion. First, let's analyze the balloon with impeller. It produced a deeper vortex, which indicates stronger fluid circulation. It also achieved complete mixing in a shorter time frame. The higher level of turbulence it generated resulted in vigorous agitation, which promoted better particle dispersion and a more uniform distribution throughout the liquid. Ultimately, it exhibits a higher overall mixing efficiency and produced a more homogeneous mixture. On the other hand, the spring disc impeller produced a shallower vortex due to weaker fluid circulation. Consequently, it required a longer time to achieve complete mixing. Because it generated lower turbulence, the resulting agitation was gentle. This caused the particle to remain near the bottom initially before gradually dispersing. As a result, the spring disc showed lower mixing efficiency and a less homogeneous mixture. In conclusion, the balloon with impeller proved to be much more effective choice for meeting our mixing uniformity goal under this parameter.
Of rotational speed of mixing performance was investigated while maintaining constant condition, including 1200 ml liquid volume, balloon with impeller, vertical shaft position, and the same immersion depth. At the low speed, the impeller generates low energy input, resulting in weaker fluid movement, lower turbulence, and limited circulation. At medium speed, the impeller provides moderate energy transfer, producing better circulation and more balanced mixing condition. At high speed, stronger turbulence and fluid circulation was achieved due to the higher energy input and centrifugal force. However, the active vortex formation may lead to splashing. Therefore, medium speed was considered the most suitable condition as it provided effective mixing while maintaining stable fluid behavior. Based on the observation, the increasing rotational speed improved fluid movement and mixing performance. Higher speed increased turbulence and liquid circulation due to the greater energy transfer from the impeller. At low speed, weak circulation and small vortex were observed because insufficient energy input. Medium speed produced a more stable vortex and provided balanced mixing efficiency. As the speed increased, vortex depth also increased due to the stronger centrifugal force, which caused the liquid surface to move downwards. However, excessive turbulence at high speed resulting in splashing due to the strong fluid agitation. Overall, medium speed was considered the most suitable condition as it provided effective circulation while maintaining mixing stability.
We have put spring disc impeller at 3 distinct submerged depths. At the shallow depth, the proximity to the surface generates a wide shallow vortex. This configuration caused significant surface disturbance and strong air entrapment though it proved inefficient for mixing, as the bit remained primarily at the bottom of the char. Second, transition to the mid-depth. We observe a narrow vortex formation, poor surface disturbance and air entanglement moderate, resulting in optimal environment that achieves significantly better bit distribution throughout the fluid. Finally, at the deep level, the vortex became thin and elongated. While this position minimized surface disturbance and air entrainment, it shifted the bit movement, causing them to concentrate specifically around the impeller rather than dispersing.
Next is test 5, which investigate the effect of shaft angle on mixing performance. In this experiment, the impeller type, speed and depth were kept constant, while the shaft position was changed to off-central, incline and side impelling. The off-central position produced a moderate vortex, fast mixing time and good circulation throughout the vessel, resulting in relatively uniform mixing. The incline position gave the fastest mixing time and the highest turbulent level. The combination of axial and radial flow helped distribute the fluid more evenly and reduce jet zone. Meanwhile, the side entering position produced a shallow vortex and longer mixing time. Since the fluid was concentrated near the vessel wall, mixing was less uniform and some jet zones were observed. Based on the result, the off-central shaft position showed the best overall mixing performance. Its position allowed energy and fluid circulation to be distributed more evenly throughout the vessel. A stable vortex was formed, helping to minimize jet zone and produce faster and more uniform mixing. In contrast, the incline and side entering position resulted in less inflection mixing. The flow pattern became less uniform, circulation weakened in some regions, and vortex formation was less stable. As a result, mixing performance was lower compared to the off-central shaft position. This slide summarizes the best mixing condition obtained from all 5 experiments. First, the 2000 ml volume showed the best mixing performance because it produced a deeper vortex, stronger fluid circulation, and a shorter mixing time compared to the other volume. Second, the balloon with impeller achieved the most effective mixing. Its design generated higher turbulence and better particle dispersion, resulting in a more homogeneous mixture within a shorter time. Third, the medium speed was identified as the optimum operating speed. It provides a stable vortex and efficient fluid circulation without causing excessive turbulence or splashing that occur at higher speed. Next, the mid-submerged depth gave the best performance by creating a narrower vortex, reducing air entrainment and promoting a more uniform distribution of the bits throughout the vessel. Finally, the inclined shaft orientation was selected as the best shaft position because it produced the faster mixing with high turbulence and minimal dead zone, leading to the most efficient and uniform fluid circulation. Overall, the combination of 2000 ml volume, balloon with impeller, medium speed, mid-submerged depth, and inclined shaft orientation represent the best mixing condition for achieving efficient and uniform mixing.
Moving to recommendation, we recommend analyzing how fluid viscosity alters circulation pattern, optimizing the shaft angle and depth for data reproducibility, and upgrading to precise numerical RPM control to find the most energy efficient setting. Finally, as concluded in this experiment, the study successfully established how key parameters influence mixing, characterize the shifting dynamic of vortex behavior, and identify the optimal configuration needed to achieve a perfectly uniform blend with minimal power consumption.